All right, this is Chapter 8 on torques. We're going to cover a number of different topics here, and really, Chapter 8 is going to include everything from Chapters 2 all the way up to 7. Including Chapters 2 through 6. So we'll deal with Newton's second law. Uh, we'll deal with energy, momentum, all that business that we've been dealing with, except now it's going to be in a rotational frame. We're going to deal primarily with torques. A torque is any time that you exert a force at a certain distance. So this comes up, for example, with torque wrenches. Like if I have a wrench, it rotates about, say, this axis, and I apply a force right there. We call this distance the distance r. That's called the moment arm. And it's just the distance at which the force is applied from the axis of rotation. Torques always cause rotation. And it's useful to describe torques because, well, anytime you have a rotating object, at some point there's been a torque that has acted on that object. And so rotation occurs in a lot of different things, whether they be in biological systems or physical systems. We see rotation quite a bit in the world. Now, Newton's second law, remember F equals ma, also extends to rotational motion. And just like forces cause acceleration, torques now cause angular acceleration. Angular acceleration. And if you remember, the value that we have for that is alpha. And so you can think of a torque then as an angular force of sorts. If we're thinking about this analog between rotational motion and linear motion, remember we had these linear quantities, x, v, a, and now we also have f as linear quantities. Well, x we had become theta, v we had become omega, a we had become alpha, and now f, these aren't equal, it's like an analog between them. F, the analog in the rotational frame, is the torque. This is the Greek letter tau. We'll use it to describe the torque. So where we were dealing with a force, we're now dealing with a torque. And Newton's second law will apply there. And when we know Newton's second law, F equals ma. If we know the torque, then we can determine the acceleration. All right. It's just a figure describing where the force is applied. So for example, here I have a force that is applied there, and the distance from where your axis of rotation is to your point of your force being applied is r, and that's actually a vector r, though that won't come up very much here. Now the magnitude of the torque is a vector quantity, and the magnitude of that torque is given by this expression, Fr sine theta. Even though torque is a vector quantity, we won't deal so much with it as a vector. We'll really just deal with the magnitude of the torque, and then also we'll deal with what is the direction of the motion that the torque causes. We calculate it in this way, Fr times sine theta, where theta is the angle between the moment arm and the force. So for example, theta is here between the moment arm and the force. Theta is not this angle, right? That is not theta, because that's not between the force and the moment arm. That's between the force and a line that's perpendicular to the moment arm. Now, when the angle between F and R is 90 degrees, then we know that the sine of 90 degrees, the sine of 90 degrees equals 1. So if these two are perpendicular, then the torque is just equal to F times R. So that occurs if I have a rotation axis rotating about here, and then I have a force that is perpendicular to the moment arm. Like for example here, this is a door. If I have a force that's perpendicular to my moment arm, that's going to give me my maximum torque. You know that the sine of theta is always less than 1, and since our torque is equal to F R sine of theta, anytime that theta is less than 90 degrees, that's going to give me some lesser torque. So if I apply a force in this direction, that will give me maximum torque. However, if I apply a force in this direction, that gives me less torque, because this angle now is smaller than 90 degrees, and the sine of theta then is smaller than 1. And then if I apply a force in this direction, well, this angle is 180 degrees, and the torque then provided by that force is 0. We know this sort of intuitively. That's why whenever we open a door, we don't push on it in this direction. We push on it in this direction because that provides the maximum torque. In fact, if we push on the end like this with an angle of 180 degrees, that provides no torque at all. You'll just look like an idiot because your door is not going to open or close or do anything. You might not look like an idiot, all right, but you'll look strange. Now, the SI unit for torque is the Newton meter. Newton meter. If you'll recall, back when we were doing work, we use the units of joules for work, but sometimes the units of work are also given in Newton meter. You remember work was force times displacement, but it's not to be confused with torque here. It's not the same thing. So it's definitely not the same as work. And that's why we use joules for work back then. But some people use Newton meters for work as well. Anyway, so the SI unit for torque is Newton meters. If you were to express this in its basic SI units, it would be kilogram meters per second squared. That's newtons, right? Force is mass times acceleration, times my meters. So I just add a second meters there. So it's kilogram meter squared per second squared. Now, clockwise torques, as we've talked about, this is the same in our right-handed rotational frame. We're using a right-handed coordinate system, meaning that if you hold your hand in front of you, your index, your ring finger, your index, your middle finger, and your thumb would be like the axes of our right-handed coordinate system. Anyway, clockwise torques are negative, and counterclockwise torques are positive. So the units for rotation, or the signs for these rotational directions, are the same as what we had in the previous chapter. Now, in order to have static or equilibrium conditions, we have to meet two criteria. And if you're pre-engineering, you'll have a whole course on this. Now, we already had one of these equilibrium conditions that we used in Chapter 4, and that was that in order for something to be in equilibrium, the sum of all the force vectors has to equal 0. But there's another criterion that has to be met in order to have a system in equilibrium. And that didn't come up in Chapter 4 because there were no rotating bodies. But when you're building large structures or buildings or whatever, you have the existence of these moment arms, things that can rotate around other axes. And so you also have to consider this equilibrium condition, not only that the sum of the forces has to equal 0, but the sum of the torques has to equal 0. All right, we're going to work through some problems, and in your quiz coming up, you'll have to figure out what is the sum of the torques. Let me just show you a quick example. Let's say that I have an object that's rotating about this point right here. And let's say that I have a force of 2 meters right here. That is 1 meter, or excuse me, not 2 meters, 2 newtons. That is 1 meter from the axis of rotation. And then I have another force of 2 let's call this 3 newtons. That is, say, 3 meters from the axis of rotation. All right, these are two torques. I'd call this torque 1. I'd call this torque 2. The sum of the torques then would be torque 1 plus torque 2, but one of these torques is negative. Remember, anytime you have clockwise motion, that is a negative direction, or is a negative torque. This force is going to cause the bar to move in that direction, in the clockwise direction. So my sum of my torques will be negative torque 1, negative because it's clockwise, plus torque 2. Torque 2 would cause the bar to go in this direction, which is counterclockwise, so torque 2 is positive. All right, so I can do that if I just put in my numbers here. Now my sine of my theta in both of these cases is 90 degrees, so I'm just going to leave off the sine of theta. So it's going to be negative 2 newtons times 1 meter plus 3 newtons times 3 meters. That's 9 minus 2 is 7 Newton meters. And it's positive 7 Newton meters. That means that that torque causes a counterclockwise motion. And you probably could have looked at this just to see, you know, that this force is bigger. Not only is it bigger, but it's at a larger moment arm, and so it's going to provide a much larger torque, right, by a factor of, well, 4.5 or so. All right, so it has a larger torque, so it dominates in the rotation and causes the rotation to go counterclockwise. Let's stop there. You're going to do a very similar thing here where you find the net torque. I'll let you do that in your online quiz. You can go and fill it out. And then you're going to do something similar here. If you're in the lab, you did a whole lab experiment on this where you're balancing the torques. Where can Kaisa stand to balance the board? We'll pause there and pick back up in just a bit.